Well, hello and welcome to our monthly webinar. I'm Tom Sandry, the Director of Workforce Development at Vector Power, and in this month's webinar, we're going to master insulation resistance testing. So, without further ado, let's get started. In our webinar, we will review insulation and its properties and the basic causes of insulation degradation. The topics are going to include what is electrical insulation and what are the properties of dielectric insulation? What causes the insulation to degrade? How is insulation resistance measured? How does an insulation tester or Megohmmeter operate? What are the types of tests that you can perform with an insulation test set? How do I obtain quality measurement results? And finally, are there safety concerns when using an insulation resistance test set? All right, let's start with what is electrical insulation. An electrical insulator is a non-conductive material that provides electrical isolation between two parts at different electrical potentials. To achieve this, the insulator must meet two main requirements. It must have sufficient electrical resistance and dielectric strength for the specific application. Secondary requirements pertain to the material's thermal and mechanical properties. Sometimes additional considerations related to dielectric loss and dielectric constant must also be considered. Another important requirement is that the material's properties do not deteriorate in the intended environment over its desired lifetime. Electric insulation is a crucial factor in the technical and economic feasibility of complex electric power systems. The performance of electric power generation, transmission, and distribution depend heavily on it. The basic difference between a conductor and an insulator or dielectric is that free charge has high mobility in a conductor. In contrast, free charge has little or no mobility in a dielectric. Dielectric strength measures the electric stress required to move a substantial charge through a dielectric abruptly. It deteriorates with the ingress of water and with elevated temperatures. For high voltage applications, dielectric strength is the most important single property of the insulation. Insulation resistance measures how much current is drained away from the conductor through the bulk or along the surfaces of the dielectric. All insulators may be classified as either solid or fluid. Solid insulation is further divided into flexible and rigid types. Flexible insulation is generally thermoplastic and commonly used for electric power cables. Thermoplastics are initially soft and can be extruded by using only pressure. Examples of these extruded dielectrics include polyethylene or PE, cross-linked polyethylene XLPE, and ethylene propylene rubber or EPR. Cellulose paper insulation is neither thermoplastic nor thermosetting. It is widely used in cables, transformers, and rotating machines in multi-layers and impregnated with oil. Rigid insulation includes glass, mica, epoxies, porcelain, alumina, and other ceramics. Rather than being used to insulate wires and cables, except for mica, these materials are used in equipment terminations, potheads, and as support insulators in tension or compression for overhead lines whose primary dielectric is air. These rigid structures must be shock resistant, be relatively water impervious, and be able to endure corona discharges over their surfaces. Liquids, gases, and vacuums are all fluid insulation. For all of these, the electrical structure must contain the fluid in regions of high electric stress. Fluid insulators are used in very high power, high current devices where solid insulation and a heat sink would be too bulky, or where a very large amount of waste heat must be removed from a relatively small area. Next, let's focus on dielectric material. Dielectric material refers to nonconductors or insulators in which an electric field can be sustained with minimum power dissipation. Unlike metals, no electricity flows in dielectrics when placed in an electric field. Instead, dielectric polarization occurs. When a dielectric is placed in an electric field, electric charges do not flow through the material as in a conductor, but only slightly shift from their average equilibrium positions, causing dielectric polarization. This produces an internal electric field, reducing the dielectric's overall electric field. So, what are some considerations for dielectric materials? Well, an important consideration for a dielectric material is its ability to support an electrostatic field while dissipating minimum energy in the form of heat. This dissipated heat or energy loss is known as dielectric loss. The lower the dielectric loss, the more influential the substance is as a dielectric material. Another consideration is the dielectric constant, the extent to which a substance concentrates the electrostatic flux lines. Substances with a low dielectric constant include a perfect vacuum, dry air, and most pure dry gases like helium and nitrogen. Materials with moderate dielectric constants include ceramics, distilled water, paper, mica, polyethylene, and glass. Metal oxides in general have high dielectric constants. Let's do a comparison of dielectrics versus insulators. Dielectrics can develop an internal electric field which nullifies the externally applied voltage. Insulators do not develop an internal electric field. Dielectrics are easily polarized and can store charges. Insulators actively obstruct electricity. Dielectrics contain relatively weak bonds within atoms. Insulators contain strong covalent bonds. And dielectrics are mainly used in capacitors, power cables, transformers, and resonator oscillators, where insulators are used in high voltage line systems and electrical appliances to prevent users from getting electric shocks. Okay, so what causes insulation to degrade? Well, let's start with electrical stress. Insulation is designed for a particular application. Overvoltages and undervoltages cause abnormal stresses within the insulation, which can lead to cracking or delamination of the insulation. Also, mechanical stress. Mechanical damage, such as hitting a cable while digging a trench, is fairly obvious, but mechanical stresses may also occur from running a machine out of balance or frequent starts and stops. The resulting vibration from machine operation may cause defects within the insulation. Another consideration is chemical attack. While you would expect insulation to be affected by corrosive vapors, dirt and oil can also operate to reduce the effectiveness of insulation. Thermal stress. Running a piece of machinery in excessively hot or cold conditions will cause overexpansion or contraction of the insulation, which might result in cracks and failures. However, thermal stresses are also incurred whenever a machine starts and stops. Unless the machinery is designed for intermittent use, every stop and start will adversely affect the aging process of the insulation. Continuing on the topic of thermal stress, heat dissipation is an important factor when considering ampacity. If heat cannot dissipate, the insulation begins to heat up and can lead the insulation into a thermal runaway. For example, the thermal resistivity, or the rate at which a specific material can resist heat flow, differs for each cable component and the medium around it, which can be ductwork or the environment. If the thermal resistivity of a material is low, then the heat can dissipate quickly. Finally, we need to consider environmental contamination. Environmental contamination covers a multitude of agents ranging from moisture from processes to humidity on a muggy day, and even attacks by rodents that gnaw their way into insulation. So, how is insulation resistance actually measured? Insulation resistance is measured with an insulation resistance test set called a Megohmmeter, or simply Megger. Several manufacturers of insulation resistance test sets exist, such as the company Megger, AEMC Instruments, Fluke, and Metrel. An insulation resistance tester is a portable instrument that directly measures insulation resistance in ohms, megohms, gigohms, or even teraohms, regardless of the test voltage selected. For sound insulation, the resistance usually reads in the megohms or higher ranges. It is a high-range resistance meter or ohm meter with a built-in DC generator. The instrument's generator, which can be hand crank, battery, or line operated, develops a high DC voltage that causes several small currents to flow through and over the surfaces of the tested insulation. The ohm meter measures the total current and has an analog indicator scale, a digital readout, or both. Some insulation testers have 2 terminals, while others have 3. As these are DC testers, 2 terminals are the positive and negative. The third, if present, is a guard. It does not have to be used, and many operators use insulation testers satisfactorily without ever employing the guard terminal. However, it affords the operator an extra function for diagnosing equipment problems. The guard is a shunt circuit that diverts surface leakage current around the measurement function. If parallel leakage paths exist, a guard connection will eliminate those from the measurement and give a more precise reading of the leakage between the remaining elements. Let's talk about connecting an insulation test set. DC high potential test sets and megohmmeters are fairly common test sets used by high voltage technicians and engineers. The basic operation for both a DC high potential test set and a megohmmeter is the same. A known DC voltage is applied across insulation. The applied potential causes several small currents through and over the surface of the insulation being tested. The total current is measured, and the result is displayed as either an ohmic value or as a current value. With modern insulating materials, there is little if any difference in the readings obtained regardless of the way the terminals of the test set are connected. However, did you know that connecting the positive lead to the ground is the industry standard? The output polarity of DC high potential test sets is designed to be negative polarity, positive ground. The reason for this is that on older insulation, a little-known phenomena called electrodosmosis causes a lower insulation reading to be obtained with the positive terminal connected to the ground side of the insulation being tested. Since insulation testing is typically concerned with safety, maintenance, and troubleshooting, the worst case reading would be the one that yields the most relevant information. Also, negative polarity is preferred since water molecules are positive polarity and are attracted to the negative voltage, giving a more comprehensive picture of the insulation condition. Unlike DC high potential test sets, most Megohmmeters on the market do not have fixed leads. Instead, they provide a positive and a negative test terminal. If the user doesn't know any better or doesn't read the manual, if the information is in the manual, he or she most likely uses positive polarity. Now, as stated earlier, with most modern insulation, it makes little difference. Still, with older insulation and many wound devices, motors, and transformers and such, it does matter when trying to obtain consistent readings. Let's talk about the components of test current. If we apply a test voltage across a piece of insulation, then by measuring the resultant current and using Ohm's law, resistance equals voltage divided by the current, we can calculate the insulation's resistance. Unfortunately, more than one current flows, which tends to complicate matters. The total current that flows during an insulation resistance test is made up of three main components. First, we have the capacitive charging current. The current required to charge the capacitance of the insulation being tested is initially large but relatively short-lived, dropping exponentially to a value close to zero as the item under test is charged. Insulating materials become charged in the same way as a dielectric in a capacitor. Next, we have absorption or polarization current. Absorption current, which is the current drawn into the insulation by the polarizing of the electrons, is initially high but drops over time, at a rate slower than the charging current. And finally, we have conduction or leakage current. The conduction or leakage current is the small, steady-state current that divides into two parts. One, the conduction path through the insulation, and secondly, the current flowing over the surface of the insulation. Now, let's look at some typical hookup connections for various test specimens. When connecting to a single conductor cable to measure the insulation resistance of the conductor to the ground, make the following connections. Connect the Megohmmeter's positive, the earth terminal, to the cable's sheath or neutral. Next, connect the test set's negative or line terminal to the cable's conductor under test. When testing a multi-conductor cable, if you wish to measure one conductor to all other parts, make the following connections. 1. Jumper two of the conductors together. Next, jumper the two conductors to the cable's sheath or neutral. Third, connect the positive or the earth terminal to the cable's sheath or neutral. And finally, connect the negative, the line terminal, to the conductor of interest. When testing a multi-conductor cable, if you wish to measure one conductor to earth or ground, make the following connections. 1. Jumper two of the conductors together. Second, connect the positive or the earth terminal to the cable's sheath or neutral. Third, connect the negative, the line terminal, to the conductor of interest. And finally, connect the guard terminal to the remaining two conductors. The function of the guard was discussed earlier in our webinar. Anything connected to the guard will bypass the measurement circuit and will not be measured. When testing the multi-conductor cable, if you wish to measure one conductor to the other conductors minus the ground, make the following connections. 1. Jumper two of the conductors together. Second, connect the positive, the earth terminal, to the other conductors. Third, connect the negative, line terminal, to the conductor of interest. And finally, connect the guard terminal to the cable's sheath or neutral. Once again, anything connected to the guard terminal will bypass the measurement circuit and will not be part of the final measurement. Under the electrical tests required on a three-phase transformer, either dry type or liquid filled, the International Electrical Testing Association, or NETA, requires insulation resistance tests be performed winding to winding and each winding to ground. To perform the high voltage winding to low voltage winding and ground test, connect the Megohmmeter as follows. 1. Jumper H1, H2, and H3 together. Second, jumper XO, X1, X2, and X3 together, and jumper XO to ground. Third, connect the Megohmmeter's positive, the earth terminal, to the X windings. And finally, connect the Megohmmeter's negative or line terminal to the H windings. To perform the high voltage winding to ground with low voltage winding to guard test, connect the Megohmmeter as follows. 1. Jumper H1, H2, and H3 together. Second, jumper XO, X1, X2, and X3 together. Third, connect the Megohmmeter's positive, the earth terminal, to ground. Fourth, connect the Megohmmeter's negative or line terminal to the H windings. And finally, connect the guard terminal to the X windings. To perform the low voltage winding to high voltage winding and ground test, connect the Megohmmeter as follows. Again, jumper H1, H2, and H3 together, and jumper H1 to ground. Next, jumper XO, X1, X2, and X3 together. Then, connect the Megohmmeter's positive or earth terminal to the H windings. And finally, connect the Megohmmeter's negative or line terminal to the X windings. To perform the low voltage winding to ground and high voltage winding to guard test, connect the Megohmmeter as follows. Jumper H1, H2, and H3 together. Jumper XO, X1, X2, and X3 together. Connect the Megohmmeter's positive, the earth terminal, to ground. Connect the Megohmmeter's negative, line terminal, to the X windings. And finally, connect the Megohmmeter's guard terminal to the H windings. Our last test will be to perform the high voltage winding to low voltage winding test. and we connect the Megohmmeter as follows. Jumper H1, H2, and H3 together. Then connect the Megohmmeter's positive or earth terminal to X3. Connect the Megohmmeter's negative or line terminal to the H windings. Now let's look at connecting to a circuit breaker. There are various insulation tests performed on a circuit breaker. Some of these tests are performed with the breaker in the open position, and some are performed with the breaker in the closed position. The table shown here will give an example of the various tests and what elements of the breaker's insulation will be tested. Let's start with the line and load stabs to ground tests. To perform these, the circuit breaker is placed in the open position, and there will be a total of 6 readings. Connecting the Megohmmeter, we take the negative lead and connect it to the line side of the first phase, and the positive lead to ground. For our second measurement, we would connect to the load side of the first phase and to the equipment ground. Moving on to the next phase, we repeat the process. So our third measurement would be from the line side of the next phase to ground, as seen here. The fourth measurement is the load side to ground. Moving on to the last phase, we simply repeat the process again, taking our measurement from the line side to ground, as seen here, and then taking a measurement of the load side of our last phase to ground. The next in our series of measurements, we will look at the line stabs to load stabs. Again, the breaker is in the open position, and there will be a total of 3 tests performed. First, we measure from the line to the load. Moving on to the next phase, we once again repeat the process and measure from the line to the load. This process is repeated once again when we move to the last phase, again connecting between the line and the load. Our next series of measurements will be to measure the line stab to ground. To perform this test, the breaker is now placed in the closed position, and once again there will be a total of 3 tests performed. First, we connect the negative or line terminal to the line side of the breaker, and the positive or ground lead to the ground or frame of the breaker. Moving on to the next phase, we simply repeat the process as seen here. And finally, we move on to the last phase, once again repeating the process as seen here. For our last set of measurements, we will look at phase to phase. And once again, the breaker is in the closed position, and there will be a total of 3 tests performed. First, we measure from phase 1 to phase 2, as seen here. Next, we will measure from phase 2 to phase 3, as seen here. And finally, we will measure from phase 3 to phase 1, as we see here. Now let's talk a little bit about the types of tests that we can perform. Let's start with the spot reading. The spot reading test is the simplest of all insulation tests. The test voltage is applied for a short, specific period, typically 60 seconds, as usually any capacitive charging current will have decayed by this time, and a reading is then taken. The reading can then be compared to the minimum installation specifications. Spot readings can be performed as part of an inspection or as part of troubleshooting and can be used as a simple good-bad indicator. Spot test readings can also be trended against previously obtained values. However, insulation resistance is highly temperature dependent, and thus the results should be corrected to a standard temperature. When reviewing the test data, the insulation was good if the insulation resistance reading was high and if it increased or remained steady during the test. Current decreases as insulation resistance increases. If the insulation resistance reading decreased during the test, the specimen's insulation would probably be wet or otherwise in bad condition. If the final value is low or the current is high, the specimen's insulation could be better. If readings are to be trended, a temperature correction must be applied. We can refer to the International Electrical Testing Association, or NETA, Table 100.14.1 for insulation resistance conversion factors to 20 degrees Celsius, or Table 100.14.2 for insulation resistance conversion factors to 40 degrees Celsius. The next test that we will review is the polarization index, or dielectric absorption test. A valuable property of insulation that must be understood is that it charges during a test. The polar DC field the tester applies causes the insulating material to realign on the molecular level as dipoles orient themselves with the field. This movement of charge constitutes, of course, a current. Its value as a diagnostic indicator is based on two opposing factors. The current dies away as the structure reaches its final orientation. At the same time, leakage promoted by deterioration passes a comparatively large constant current. The net result is that with good insulation, leakage current is relatively small, and resistance rises dramatically as charging goes to completion. This changing resistance is precisely what an experienced technician wants to see. Deteriorated insulation will pass relatively large amounts of leakage current at a constant rate for the applied voltage. This will flood out the charging effect. Time resistance methods, as they are known, take advantage of this charging effect. Graphing the resistance reading at time intervals from the initiation of the test yields a smooth rising curve for good insulation, but a flat graph for deteriorated equipment. The ultimate simplification of this technique is represented by the popular polarization index, PI, and the dielectric absorption, or DA, tests, which require only two readings and a simple division. Performing the PI test, the 1-minute reading is divided into the 10-minute reading to provide a ratio. In dielectric absorption, or DA, the time values are typically 30 seconds and 60 seconds. A low ratio indicates little change, hence poor or contaminated insulation, while a high ratio indicates the opposite. References to typical PI values are standard in literature, which makes this test very easy and readily employed. Resistance readings alone are difficult to work with, as they may range from enormous values in new equipment down to a few megohms just before removal from service. A test like the PI is instrumental because it can be performed on even the most extended cables, yielding a self-contained evaluation based on relative readings rather than absolute values. The polarization index test is a famous test that is performed on rotating machinery. It is called out in various testing standards. The next test that we're going to look at is the step voltage test. Since good insulation is resistive, an increase in test voltage will lead to a rise in current because the resistance remains constant. Any deviation from this could signify defective insulation. These defects might be unobserved at low test voltages, say 500 volts or 1000 volts. Still, as the voltage rises, we reach a point where ionization can occur within cracks or cavities, increasing current and therefore reducing the insulation resistance. Note that it is unnecessary to get the design voltage of the insulation for these defects to become apparent, since we are simply looking for ionization in the defect. The step voltage test follows precisely this principle and can be employed at voltages reaching 2,500 volts and upwards. The step voltage test may be used as an undervoltage or overvoltage test. However, it must be remembered that an overvoltage test can lead to a catastrophic failure if the insulation breaks down because high voltage test sets, such as high potentials or high pots, have a lot of power available. An undervoltage test carried out by an insulation resistance tester has relatively little power available and is far less likely to result in a destructive test. A recognized standard procedure is to increase the voltage in 5 equal steps at 1-minute increments and record the final insulation resistance at each level. Any marked or unusual resistance reductions is an indication of developing weaknesses. Now let's talk about potential sources of errors obtained in our measurements. Beware of low-quality leads whose voltage rating is less than the test voltage that's being employed. It is extremely important that the only leakage currents during a measurement are those developed by the insulation under test. If the leads produce leakage, you may measure lead insulation resistance rather than the item under test. Test leads should not be allowed to touch each other or any other object, since this will induce leakage paths. Sharp points at the test lead connections should be avoided, since this will encourage tracking. Another area that can be confusing is that insulation resistance measurements are typically line to ground measurements. Therefore, understanding series and parallel circuits is essential when evaluating test results. Here is a typical example that can cause confusion to a technician. Let's say we're measuring the insulation resistance of a section of bus duct or perhaps a section of cable. First, we measure the individual sections of the bus or possibly cable. Next, we will connect the bus sections together. When we connect the sections, we create parallel resistances, and their values are added as reciprocals. So, in this example, what should we measure? When we add the insulation resistance values as reciprocals, we can see here that the total resistance of the assembled bus run equals 5 megohms. Now, measurements of bus duct or cable runs should also be corrected to a nominal length. For example, using the following formula to determine the minimum insulation resistance value in megohms to a 100-foot nominal value, the minimum megohm value would equal 100 divided by the busway or cable length in feet. As we can see, adding sections or length introduces more parallel paths. Insulation resistance test voltages and minimum insulation resistance values shall be based on the manufacturer's published data. Insulation resistance values will be corrected to a nominal 100-foot busway run without the manufacturer's published data available. Using the following formula to determine the minimum insulation resistance value in megohms to a 100-foot nominal value. Again, that formula is minimum megohm value equals 100 divided by the busway length in feet. Adjusted to 1,000-foot nominal value, we would use the formula. The 1,000-foot nominal value equals measured insulation resistance times length of the run divided by 1,000. The converted insulation resistance values less than the manufacturer's minimum or less than the corrected minimum megohm value should be investigated. When performing electrical testing, we temporarily energize the circuit with a test potential or voltage. The device under test is now energized and presents an electric shock hazard. Energy control safe work practices must be followed to mitigate this hazard. If testing cables or sections of bus run, electrical shock approach boundaries must be established at both ends of the cable or bus run to create a safe test area for workers. Also, an energized cable can create capacitive coupling to adjacent cable phases. To prevent capacitive coupling, cable phases that are not energized or tested must be grounded. A shock hazard is a source of possible injury or damage to health associated with currents through the body caused by contact with or approach to energized electrical conductors or circuit parts. Current through the body causes electric shock or electrocution. The potential difference a person may make between a conductive part of equipment or between the equipment and the ground is essential because this voltage forces current through the body according to Ohm's law. Therefore, current through the body increases with lower resistance and contact voltage. Dalziel's equation gives the maximum safe body current for short periods of time, which is an inverse function of time. Higher currents are permitted for shorter periods. In the equation, we see I sub k equals k divided by square root of t, where I sub k is the maximum safe body current in milliamps. T is the shock duration. K is a factor for body weight. Shock currents below the threshold determined by this equation, although not lethal, may be painful and cause involuntary movement. Pause the video and take some time to review the table shown for different current levels and the possible effect on the human body. As an informational note, most DC insulation resistance test sets, Megohmmeters, offer output currents of 3 to 5 milliamps. Also, a power factor test set, such as a Doble M4000 or an AC high potential test set, can put out between 100 milliamps to 300 milliamps of current. Now that we're more aware of shock hazards, let's discuss the safe limits of the approach. As we should have learned during our electrical theory classes, energized circuits or circuit parts produce electrostatic fields. These fields are created by voltage, and the two have a causal relationship, which means that the higher the voltage, the greater the electric field. Any circuit interaction within these fields can lead to electric field induction, also known as capacitive coupling. Electric field induction generates voltages or currents to the ground or both in a conductive object or electric circuit by the time-varying electric fields. Since these fields have a causal relationship with voltage, approach boundaries for safety have the same relationship. Higher voltages require greater distances for safety. Remember, you don't necessarily need to come in contact with those energized circuits or parts for them to arc across and give you a shock. The NFPA 70E, Standard for Electrical Safety in the Workplace, defines two approach distances based on voltage. They are the limited approach and the restricted approach. Let's first look at limited approach. This is an approach limit at a distance from an exposed energized electrical conductor or circuit part within which a shock hazard exists. This boundary is determined based on the nominal phase-to-phase voltage of the energized conductor or circuit part. Unless needed, no unqualified person shall be permitted to approach nearer than the limited approach boundary. The restricted approach is an approach limit at a distance from an exposed energized electrical conductor or circuit part within which there is an increased likelihood of electric shock due to electrical arc-over combined with inadvertent movement. This boundary is determined based on the nominal phase-to-phase voltage of the energized conductor or circuit part. These boundaries, as used in the NFPA 70E, establish safe distances and awareness when working around energized circuits or circuit parts. They can also assist us in establishing a safe test area when we apply test voltages to equipment. Let's review some safe work practices whenever we are applying test voltages. Obtain and review up-to-date drawings and prints of all circuits to be tested. If up-to-date drawings and prints are not available, circuits must be traced out and documented prior to applying temporary voltages. The temporary application of voltages cannot proceed until the circuit path, potential backfeeds, affected gear, and circuit access areas are known and factored into the shock hazard assessment and temporary energy control plan. When applying voltage to a circuit, you must treat all parts, such as a transformer bushing, as energized. You must establish limited and restricted approach distances based on the applied voltage. When testing circuits, you must first verify where the voltage is going. For example, verify both ends of cables. You must know the circuit path 100% prior to applying energy. Before the test, you must barricade all access points. In high traffic areas, barricades may not be enough to keep people out safely, and an attendant should watch all access points. Many people fear the electrical output of their insulation tester, which may be 5,000 or 10,000 volts. However, the instrument's current is generally limited to a few milliamperes and presents a relatively low hazard. The danger here is not so much the output of the Megohmmeter, but more the working environment. If the connected load is capacitive in nature, this can provide very significant energy when charged to high voltage by the Megohmmeter and can be lethal if touched. Additionally, when testing insulation in many high voltage environments, it is not uncommon to climb ladders to reach connections on equipment such as transformers, with associated risk of working at height. In such situations, an otherwise harmless electrical impulse may cause the user to react automatically, with a potentially serious injury from a fall. Fully insulated clips on the test leads and proper PPE help minimize this risk. Before making insulation test connections, the circuit under test must be switched off, de-energized, isolated, and checked to ensure safety. The circuit must not be re-energized while the instrument is connected. Circuit connections must not be touched during an insulation test. After completing a test, capacitive circuits must be fully discharged before disconnecting the test leads. Capacitive charges can be lethal. After discharge, tested items should be firmly shorted out with a shorting link until required for use. This is to guard against any stored dielectric absorption charge subsequently being released, thereby raising the voltage to potentially dangerous levels. And that concludes our webinar today on mastering insulation resistance testing. I'd like to thank you for attending our webinars each month. If you like the content that we produce, please show your support by hitting the subscribe, hitting the notify bell so that you are notified each month of upcoming content, and remember to hit that like button. It definitely helps out with the YouTube algorithms, and it helps to support the channel and allows us to provide this content for you. So until next month, be safe out there.